Hi everyone, the next topic is on the topic of differentiability. Differentiability is something that we've already discussed a little bit, including class discussions. The idea of differentiability is fairly simple, but there are details. There are aspects you have to pay special attention to that are non-obvious. Given a function f of x, no matter what I give you, you'll be able to tell me what f prime of x is. But what you may not be able to do is tell me what f prime of x is at any particular x coordinate. I may ask you to plug in an x coordinate that you can't plug into the function, or rather you can't plug into the derivative of the function because it's not in the domain. It would result in taking the square root of a negative number or in dividing by 0 or other problems. One of the big mistakes that's made is when asked where does a function have a problem with the derivative, it's often left or often interpreted as any place where the function has a problem with the domain. And that's not true. To illustrate that case, here's a function f of x is the cube root of x, which can be written as x to the power 1/3. This function, this cube root function, has a domain of all real numbers. You can plug anything you want, including negatives. For example, what is the cube root of -8? Which means what number multiplied by itself 3 times gives you -8? The answer is -2. You can plug in negatives, you can plug in positives, you can plug in 0. This function takes everything. Even though its domain is all numbers, it has a problem with the derivative. If you take the derivative with the power rule, so the power comes down, we have x to 1 lower power, that becomes power -2/3. We can use exponent laws, bring that x down to the denominator with a positive 2/3 power, and then realize that this derivative has a problem at 0. We can't plug x equals 0 in. We would end up dividing by 0. So even though the original function contains 0 in the domain, the derivative of the function does not contain 0 inside its domain. That means that this function has no derivative there. Now, we said derivatives are instantaneous rates of change, the slope of a tangent line. And does that mean this function doesn't have a tangent line there? So in the bottom right is the graph of that function we were just talking about, x to the power 1/3. What's happening is at this coordinate, at x is equal to 0, the tangent line is going vertical. It's going straight up and down. And what's the rise over run of a vertical line? So whatever the rise is, let's say the rise is 10 or 100 or a billion, whatever it is, you're dividing by 0. If the line is vertical, it doesn't travel any amount in the x direction. So we end up having a division by 0 inside our geometric calculation of the slope of the tangent line, as we do inside our algebraic or calculus approach for the calculation of a tangent line. That's why there's a problem there. Other functions can fail to be differentiable at points. Most obvious being functions with discontinuities, because how are you going to draw a tangent line inside that region? So a line that approximates the function at a particular coordinate. There's no line that does that there. And the other type of discontinuity, the other type of non-differentiability issue you can have is for a function with a sharp corner or a cusp. So a sharp corner might be the absolute value function, which we didn't really talk about inside this class, other than, I think, showing a picture. The absolute value function has that V shape, and at the bottom of the V, there's no derivative. And there's no derivative because if you zoom in close enough, you never see a straight line. It always looks like a corner, no matter how close you zoom. So there can't be a tangent line there. Based on that, so I'll go back to it and summarize what is here. The summary is functions fail to be continuous, or there I go again. Functions fail to be differentiable at any x coordinate where there's a sharp corner, at any x coordinate where there's a discontinuity, including jumps or holes or vertical asymptotes like explosions, and locations where there's a vertical tangent, a place where the function just jumps, like not jumps, but does the abrupt increase, like what's indicated for x to the power 1/3. based on the definition of differentiability and contrasted with the definition of discontinuity, we can answer the following questions about where a function is continuous and where a function is not differentiable. So where is the top function discontinuous? There's a hole cut at x equals 4. That's a hole. And then there's a problem at x is equal to 6, and that problem is a jump. Where is it not differentiable? So it's not differentiable at x coordinates that come from two lists. The list of locations of discontinuities. So x is equal to 4 and x is equal to 6. And x is equal to 8, which is the sharp corner. So there's no derivatives at those 3 points. Next example, at what values of x is g of x discontinuous? Well, we're going to do the same thing. Look for holes, jumps, and explosions. So x is equal to -3, which is a hole. Let's cut into the function there. And then we have a jump at x equals -1. And then we have a hole at x is equal to 2. Part B, where is it not differentiable? Well, we also have some sharp corners. So it's the x equals -3, x equals -1, x is equal to 2, discontinuities. And x equals 3, x equals 4, sharp corners. So no tangent line there, thus no derivative there. There's one other topic that's been embedded in different sections of the textbook. I think perhaps even starting somewhere in chapter 2. I haven't mentioned it on purpose. I didn't test it either. The word velocity has a meaning in physics. And I don't really care to tell you what that meaning is because this is not a physics class, this is a math class. We will always interpret velocity to mean the first derivative of a function that describes an object's position. So if the position of an object with respect to time is given by f of t, the velocity of that object will be given by f prime of t. Velocity is allowed to be positive, which means an object is moving away from us, and the velocity is allowed to be negative, which means an object is moving towards us. The velocity can also be 0 if that object is not moving at all, like a desk in your room or a book on your desk. Velocities, I almost got into physics saying, well, is the desk really stationary if the Earth is, flying around the sun at a huge speed and the sun is flying through the galaxy at fast speeds and the galaxy is flying through the universe at fast speeds? Like, is anything really stationary? And the answer is no, everything's always moving. But this, again, not a physics class, it's a math class. We're allowed to say the velocity is 0 relative to whatever frame we're talking about. Anyway, who cares? Velocity can be 0. Velocity can be positive. Velocity can be negative. And how do you find velocity? You take the derivative, and sometimes you plug in a number to find what the derivative is at a particular t value or a particular x value. So a concrete example, a car's position is given by this expression 2t squared plus 20 times t plus 9. T is measured in seconds. Find the velocity of the car when t is equal to 2. So code word velocity means take the derivative. So f prime of t is equal to 4t plus 20 plus 0 using our shortcuts. Now we're going to plug in 2. F prime of 2 is equal to 4 times 2 plus 20, which is 8 plus 20, which is 28. units don't matter. Because this is not a physics class, this is a math class. If you're curious, what are the units? Well, we can't answer that question because the function doesn't tell us what the units are. The car's position is given by f of t is equal to 2t squared plus 20t plus 9 meters, kilometers, astronomical units, yards, nautical miles, centimeters, micrometers. The units aren't there. So even if it did ask for units, you just say, I can't. But you won't be asked for units, just the number. Okay, and that's it for the discussion of chain rule, differentiability, and this code word of velocity. We'll continue in the next video series on the topic of implicit differentiation.